large group notes on the universe and how the universe is changing. We're going to have a couple of videos that will get linked here. This is one that shows like what we know about our universe and all the data that we actually have. It's a really quick one. We're going to start today with looking at this image. So to understand where this image came from was if you held your hand out at arm's length and covered up something that you can see with your fingernail. It was taken from a spot of the sky that's as big as your fingernail at arm's length. Okay, and in that spot of the sky, they thought there was nothing there. And so when we get the first space-based telescope up there and they took a look, this is the image that came back. And what we learned was we didn't know a lot when we're ground-based, that there was a lot more out there that we could see. And so as we talk about the science of this, it's important to know that the science was originally formed before we could see this level of detail of our universe. So Edwin Hubble in 1929 was making these kinds of observations from a ground-based telescope. So he thought that section of the sky was empty. So he's looking at really bright galaxies, and he realizes that those dimmer ones are likely farther away. And he also noticed that those farther away galaxies had kind of a reddish tinge to them. And we call this a redshift. And a redshift happens when the light waves get stretched out as an object is moving away from us. You already have an experience with this, but we call it on Earth the Doppler effect. And you probably have heard it with sound, or you've heard it for like weather type events with weather radar. Or speed radar that a police officer might use. So let's listen to a sound example. In this sound example, I have a train, and I want you to listen to the train horn and how it sounds as it moves toward you and away from you. So you can really hear how the pitch of the sound changes. That higher pitch would be we would actually call a blue shift if we were talking about light, and that lower pitch is that red shift. We can see it in things like water. So here we have a little ducky swimming off to the right here, and you can see how the waves kind of stack up in front of the ducky and spread out over here. So if I was looking at this as a light wave, this would be blue, and this over here would be red. And we can see this kind of however we look at that. So here I have our little ducky, and when it sits there, it's just giving off those little waves all the same. But when I put the ducky in motion, what ends up happening is those waves will stack up. And so I can see those waves now. The duck is still producing waves equally spaced apart, but they're stacking up in front of the duck and they're spreading out behind the duck. So let's try it again. And if I slow the duck down, you'll notice it doesn't seem quite as severe. Like it's even hard to tell that it's stacking in front of the duck versus spreading out behind the duck. If I make the duck go really fast, you can really see it because the duck kind of makes a wake behind the duck, right? And so there's a spot to draw in your notes where you can draw those images. And so underneath the little rainbow, there's an animation example. You might want to draw something like this. So if there's a slow moving object, it's going to have a small change. And if it's a fast moving object, it's going to have a big change. So the important thing there is not only can I tell the direction that the object is moving, I can also tell the speed. So where it stacks up and where it stretches out tells me the direction that the object moves. How much it stacks up or how much it stretches out tells me how fast it's moving. So you might want to pause here and make a drawing. So here's an example. We're going to be looking at spectroscopy. So we started to look at this in lab, and what we see here is this would be like our control in the middle. It's not moving. So on your notes, you're going to want to just circle that not moving spot right there. On the top, when we compare the lines from the middle to the top, what we can see is all these lines have been shifted kind of over to the right. So that one is moving away. Whereas all these lines then in comparison have been shifted towards that purple or that blue end. So those ones are all moving toward. And so we can tell the direction that an object is moving. So then Hubble is credited for making Hubble's law. We can tell if it's moving toward or away and also how fast. So the bigger that Doppler effect, the bigger the stretch or the squish of the wave means it's moving faster. And then if it's not as apparent, if it's a smaller shift, then we know it's moving slower. And so when Hubble puts all of these observations together, what Hubble figured out was the farther a galaxy is away from us, the faster it was moving, because those farther objects had a redder shift. And we call that Hubble's law, that the farther that galaxy is away from us, the faster it is moving. And so what we then figure out is the implication of that the universe is expanding. So the traditional book example is raisin bread dough rising. So if you think about like a chocolate chip cookie or something that's baking in an oven that has, bits in it, as that starts to get bigger and expand, your cookie dough expands or rises, or your bread dough expands and rises, those raisins kind of all move away from each other. And so we know that galaxies are all moving away from each other. Well, wait, Ms. Bergman, last week we talked about galaxy collisions. That's actually an exception to the rule. Galaxy collisions are actually not that frequent when we look at the overall universe. Here's another video I will link into the to the end there, or it will be on our playlist. But here is an example of that raisin bread dough. So we start out with a loaf of dough that's 20 centimeters across, and it's going to expand to 40 centimeters. The raisins on the right start off at 10 centimeters away, and the raisins on the left start off at 5 centimeters away. And then it doubles in size, so everything gets bigger. Notice how this one on this side has to go 10 centimeters, where this one only has to go 5. Because that space is expanding, this one travels farther, faster than this guy over here does. And we see that happening in our universe too. In order for that to happen, our universe has to expand. Then the question starts is, well, where's it expanding from, right? So when we look at it from our perspective, what we see is these closer galaxies are moving slower, and these farther galaxies are moving faster. So the bigger the arrow in this image, the faster it's moving. So let's imagine that we have these galaxies that are all like lovely gridded out, and then this is how far away they are right now. This is how far away they'll be in the future. And let's say we live right here on that galaxy, right? If we layer those one on top, so if I take this image and I put it right on top of that image, this is what that starts to look like, right? This one looks like it's not moving, but these ones aren't moving very much, and these ones are moving a lot, okay? But what if I move over here and I try that same exercise over there? Well, look at that. Same thing looks like that. So it doesn't matter where I'm at in the universe, it will always look like everything's moving away from me because the whole thing is expanding. Everything is moving away from each other. So there really isn't a middle. You can either think of it that way, or you can think of it like everything is the middle. And so then, if we already know that, then that starts at, well, where did it start? That kind of leads to that question. So scientists started looking at the Big Bang. And so that theory of the Big Bang is that all matter in the universe was once in whatever that central location was, or that tiny little dough ball. And 13.7 billion years ago, there was something that started this expansion. And so all the mass in the universe began exploding outward. So we have this evidence of redshifts, but we also have this thing called cosmic background radiation. So you can think of it, if there's a bang, right, there's going to be a noise. So if I were to make a loud noise in your environment, you'd be able to turn and look to see where that noise was coming from. So scientists went looking for that noise. There should be some way for us to figure out where the middle was. And what they figured out was, again, it's coming from everywhere. It is from all sides, all directions, and it's all the same. So it's like we are inside of the boom of the explosion. So unlike being on the outside where we could hear where it comes from, we're inside that explosion, so it's coming from everywhere. So cosmic background radiation is another piece of evidence we have that says, yep, we are expanding and we're in the middle of it. Thinking about time then, how long is 13.7 billion years? Because again, we can't wrap our head around that. If the gridiron, a football field, was a timeline with the Big Bang at one goal and cavemen to now would be the width of one single blade of grass at the other end, which means we haven't been here for very long in comparison to the universe. Here's another movie that I will pull up later. This one's from NASA. Okay, so we know where we started. We know where we're at now. How's it all going to end, right? So lots of questions on that have come up. So there's kind of two competing theories. One is that we'll expand forever. We're on this route of expansion and it's just going to keep going, keep cooling off, keep expanding until everything cools off to the point that things fall apart. Or maybe that Big Bang started actually with a big crunch. And the big crunch idea is that gravity would eventually take over, the expansion would slow down, stop, and reverse, and we would eventually collide back into one point, and then maybe it all starts over again. We don't know. So then, of course, if we're going to make claims like that, we have to look for proof. So if we look for our current mass of our universe, right now that points to the expansion option. And somewhat favored by scientists right now. The mass we can observe, the mass we study in places like physics and chemistry says that that's what's going to happen. Because our observable mass says that there's not enough to make it crunch. But if we dig into that a little bit, observable mass also actually indicates that the universe, you and me, the planet we live on, should not actually exist. That there wasn't enough mass to make any of those pieces come together in the first place. So then, okay, how do we exist? That becomes the question. And so what they started to look into is this idea of dark matter. How did we start to exist if we weren't supposed to? So let's go back to this image we started with. This is visible light, and our eyeballs can only see a tiny fraction of the electromagnetic spectrum. So if we look at it again, but with X-ray vision, all of a sudden more information starts to pop out. And we see this kind of purple blob form. That purple blob represents X-ray information. So what happens is gravity will squeeze gases inside of a galaxy or a galaxy cluster, and that causes them to give off these X-rays, which we can see with other instruments. And when we start to look at that X-ray information, what we see is that there's too many X-rays coming off for how much gravity should be there based on the mass. So there's too much gravity for how much mass we can find. And so then there must be some other mass, because mass causes gravity, right? So there must be some other mass there that we can't see, so they named it dark matter. Other evidence we have that dark matter exists is when we start to look at math. If you like astronomy or you really like math, this might be a place where you can excel as in a career. But they started to look at the orbital speeds of galaxies within galaxy clusters. And so when you start to think about how things spin, right, galaxies and stars closer to the center go faster and galaxies farther go slower. But if you can get anything moving fast enough, it will reach escape velocity. That's the velocity you have to travel at which to get away from whatever has got you under its gravitational power. And what we find is that outer galaxies can be going fast enough to reach escape velocity, but these galaxies don't rip themselves apart. And so, again, there has to be some form of gravity there that we can't see. So they call that matter that's causing that dark matter. So what we do know about dark matter is it doesn't give off light or energy. We think it makes up at least 6 to 10 times the amount of matter or mass that we can see that is visible. and it should make up about 20% of the universe, 27% of the universe. The other thing that we then can infer is that there's probably dark energy, which we think makes up about 68% of the universe. So when you go to science class and you study biology and chemistry and earth space and science and physics, you're actually only studying about 5% of the known universe. That's pretty cool. And so we can't directly observe them, but we do know they exist because it's the easiest way to describe these things that we know to be like weird about our universe. And so dark matter is the unseen mass. Dark energy is whatever is causing that expansion, like why are things expanding? And so then when we start to look at that X-ray data, here's another dark matter halo, so that's the X-ray halo. You start to put those halos then into computer models and look at what it looks like. This part is so cool. So when you start to look at those individual X-ray halos and you start to look at how those galaxy and galaxy clusters connect, what does that remind you of? Just take a second and look at that picture, and what does it remind you of? Man, it could be so many different things, right? It could be nerves. Maybe it reminded you of some sort of tissue, but all of a sudden you start to realize how interconnected that huge amount of space and those huge objects are really to the rest of the universe. And so, yeah, you are connected. Not only are you made of stardust, but you are also connected to everything else in that universe. And I just think that is astronomical. All right. Have a great one, warriors.